Welcome to the deep dive. Today we're tackling something that's a real headache in modern engineering, simulation time, how long it takes to run those complex models.
Absolutely. It's a major bottleneck.
And we've got some interesting material looking at how these things called physics-informed neural networks, or PINs, might be, well, a pretty powerful way around that.
Yeah, they really are showing promise. Because look, those traditional high-fidelity simulations, they're incredibly accurate. But one run, it can take hours, days, sometimes weeks.
Weeks. Wow.
Seriously. And that just slams the brakes on exploring different designs, figuring out how changing one little thing affects everything else, or, really optimizing things properly.
Right. It's like you can only check a few spots when you need to see the whole map. So the computational cost is the big wall here.
Exactly. It limits how much you can really learn and iterate.
Okay, so that brings us to this idea of surrogate modeling, like a shortcut.
Pretty much, yeah. Surrogate models are basically faster, sort of data-driven approximations of the big, slow simulation.
So you train a machine learning model on data from the real simulation.
You got it. Instead of running the full thing every time you tweak a parameter, you ask the quick surrogate model for prediction.
Yeah.
It saves a ton of time.
Makes sense. But just using data, doesn't that feel a bit risky? Like, can you really trust a model that doesn't know the actual physics involved?
That is the million-dollar question, isn't it? And that's exactly where PNs come in. They're different.
How so?
Well, they don't just learn from the data points you feed them. They actually build the physical laws, the governing differential equations right into their training.
Okay, hold on. How do they do that? Sounds complicated.
It's clever. They're neural networks, yeah. But when they train, they get penalized for two things. Mismatching the simulation data, like normal, and for violating the physics.
Violating the physics. How does it check that?
It checks at lots of points inside the simulation domain. They call them collocation points. Basically, the model has to make predictions that satisfy the physical equations at those points. It's like built-in physics consistency checks.
Ah, I see. So it learns the data and the rules.
Precisely. And you can make them parametric, too. Just add system parameters like temperature or propitious and inputs. Then you can do super fast what-if scenarios.
Okay, this is where it gets really practical. Where are these PNN surrogates actually being used? What are the big applications?
Right. Well, there are several key areas showing real impact. First up is parametric studies.
So changing design variables and seeing what happens.
Exactly. Normally, every little change means a whole new long simulation run. With a trained PNN, you get those results almost instantly. It lets engineers explore way more options, understand sensitivities much faster. Huge speed up.
Okay, that alone sounds like a game changer for design teams. What's next?
Second, uncertainty quantification, or UQ. Real-world systems always have unknowns, right? Uncertainties in materials, conditions.
Yeah, nothing's ever perfectly known.
So PNNs can plug into things like Monte Carlo analyses. Instead of needing thousands of full simulation runs to see how uncertainties affect the outcome, you use the fast PNN. You get a much better handle on reliability and risk, affordably.
Better confidence in the design, basically? Makes sense. Number 3.
Design optimization. Finding the best design often means testing loads of possibilities.
Right. Feeding options into an algorithm.
Yeah, and if evaluating each option takes days, optimization is painfully slow. Swap in a fast PNN surrogate to evaluate the designs, and the whole optimization process just flies. Plus, PNNs give you gradients easily, which helps the optimizer find the best solution faster.
Okay, speed, UQ, optimization. What else?
Fourth is model predictive control, MPC. Think about controlling complex dynamic systems in real time, like advanced robotics or maybe process control.
You need fast predictions for that.
Exactly. PNNs can act as that fast, accurate predictive model inside the control loop, allowing for smarter, quicker decisions based on physics-aware predictions.
Interesting. Using physics-based AI for live control. Okay, and the fifth one?
Anomaly detection. This is pretty neat. You train a PIN on what normal operation looks like for a system. It learns the expected behavior and the underlying physics.
So it knows what's normal and physically plausible.
Right. Then you feed it real-time sensor data. If the data starts to drift from the PIN's predictions, or if it implies something physically inconsistent, boom, you've likely got an anomaly, maybe an impending failure. You can catch things earlier.
Like a physics-aware watchdog. Okay, 5 really solid applications there. But for someone listening, how do you know if PINs are actually the right fit for your problem? It's not magic, right?
Definitely not magic. It's a tool. You need to ask some key questions first, like, is your current simulation really the bottleneck? What's your main goal? Could maybe a simpler method work?
Good point. Don't use a sledgehammer to crack a nut.
Exactly. Then think about the problem itself. Do you actually know the governing equations? Do you want to use them? And, crucially, do you have enough data simulation results or experiments to train the network properly? There are, like, flowcharts to help decide.
So weigh the effort versus the benefit. Makes sense. And are people pushing these methods even further? What's next?
Oh yeah, the field's moving fast. People are working on better ways to handle uncertainty within the PNNs themselves, using things like Bayesian methods. Smarter ways to pick training points, active learning.
Okay.
Combining data from cheap, low-fidelity simulations with expensive, high-fidelity ones. Transfer learning, so a model trained for one problem helps with a related one. Breaking down huge, complex problems. Making models small enough for, like, edge devices. Even mixing PNs with traditional solvers. Lots going on.
Wow. Okay. So it's still very much an evolving field.
Definitely.
So to wrap up, the big takeaway seems to be that traditional simulations hit a wall computationally. Surrogate models help, but PNs offer this unique advantage by blending data with the actual physics.
That's the core idea. You get the speed benefits of machine learning, but ground it in the physical laws you know are true.
Yeah.
It's not perfect, nothing is, but it's a really powerful combination when applied thoughtfully.
So for you listening, the thought to leave you with is, where in your own work, your own engineering challenges, might this blend of speed and physical insight from PINN-ins open up new possibilities? Something to think about.
Definitely worth considering.
Thanks for diving deep with us today.